So welcome everyone to this VSS seminar by Ashish Mishra. Ashish is a faculty member at IIT Hyderabad. He did his PhD from IISc a few years back, and then he did a couple of postdocs, one at Northeastern and Purdue, and then he's finally joined IIT Hyderabad. And Ashish interests broadly in type systems, program correctness, program verification. Yeah, today he's going to tell us about using type systems for using these new kind of coverage types to give guarantees about test input generators. So welcome, Ashish, and over to you.
I think some mic is okay. So am I audible?
Yes.
Yeah, we can hear it. Yeah.
Okay. Okay. Thanks, Deepak, and thanks to the organizers for kind of giving me this chance. So I am Ashish Mishra. So today I want to present this work, in fact, series of works which are based on this underlying idea of what is called as coverage types. And so the idea is that I want to set up the foundation for coverage types, and depending on how much time remains, we will see some of the follow-up works on this. But just kind of to start, coverage types, basically the title is type-based verification for test input generators. And at least the initial portion of this work and most of today's talk was done when I was at Purdue. And I'll start with that, and then, as I said, like if time permits, in the end, I'll touch more recent extensions to this thing in the synthesis world and other places. So, just to kind of this work was done at Purdue, the major portion of this talk, and it was kind of done along with kind of remarkable student Zizou, and some of very good mentors like Ben and Suresh. So let's start by setting up the kind of context. So as the kind of title suggests, the context is in the domain of what is called as property-based testing. So for the audience for verification seminar series, I think one way to introduce could be that if we plot the verification approaches based on the amount of effort it requires to prove properties about programs against the assurances we get, then on the lower left half, we will have this approach of random testing, which requires relatively much lesser effort, but the kind of assurances it gives are also restricted. So I'm not saying that random testing hasn't been successful. In fact, it is one of the most successful approaches of formal verification in unearthing many of the real world bugs. But nevertheless, fundamentally the assurances given by this are only about the presence of bugs, and that too by kind of randomly exploring the space of inputs and the behavior of the program. On the other extreme side is what we, at least this community is more kind of akin to, is this verification, or particularly trying to prove functional correctness of programs. And here you can think of your favorite verification tool, whether it's a theorem prover or a kind of refinement types plus theorem provers like F-star, which I think earlier we have seen some talks in this seminar series itself. So where the efforts are very high, but at the same time, assurances are also quite high. So property-based testing sits somewhere in between. So where in terms of efforts, you have to put more efforts, but it also allows you to kind of use some kind of directed testing towards programs. So property-based testing, and we'll see an example of this. But it was originally proposed in the domain of for Haskell by the tool called as Quick Check, but very soon it proliferated almost all kind of main world programming languages. So let's try to see further poke this context. Okay, so further set this context. So we are particularly in the property-based testing. We also want to talk about test input generators. So what are test input generators? So the way property-based testing works is that you have a program or a set of programs, and you can define a property just like you'll define a property for other functional correctness verification approaches. Okay, so and now given this property, but unlike other approaches which will take this property and the programs into a common domain and then try to do some reasoning, what property-based testing does is that given this property, it uses test input generators to generate targeted input test cases so as to check these programs against the property. Okay, and we'll see some examples of this as well. But so in some sense, these test input generators are very important because they act as a bridge between these properties you want to test on the programs. But through these test input generators, you can generate these interesting cases. Okay, so test input generators in some sense are the core thing. So big because for a given interesting property, the kind of success of your PBT approach relies heavily on how good are your test input generators. Okay, so let us try to think what kind of properties we want or what kind of guarantees we want for test input generators. So so one of the things is that any test input generator should always generate safe test cases. Okay, so if a property requires you to generate a particular kind of test inputs, and I'll come to a concrete problem, but safety is one important thing. So every generated test must be safe with respect to the given property. An orthogonal property is that when you are kind of generating this test inputs, this has to be done in an efficient manner so as to detect more and more bugs. And there are more recent works in this direction, which basically works towards the improving the efficiency of these test input generators. An orthogonal question, though, is towards the coverage completeness. And what it means is that a test generator must generate all possible test cases satisfying a given property. Okay, so let's try to understand this with an example, the safety, the coverage, and other things. So here is how kind of a typical PBT setup look like. And I have taken a very simple program so that it is kind of approachable to the general audience. So this is a program written in an OCaml style of syntax. So this takes as an input a pair of integers, and it is a match expression which just looks at maps these x into a and b, and then does a by a minus b plus 1. A typical property will look like this. So a property is given in terms of precondition and postcondition. So what it means is that if this is the program, what we are saying is that if we assume that the input to this program are integers in the pair of integers such that both the integers are greater than or equal to 0, then the postcondition you require to verify or check or test is basically that there are no division by 0 errors. So think of this, that preconditions in the property tell you what are the inputs the generator will have to produce. And postconditions are then basically are the conditions against which you are testing the programs on these inputs. Okay. By the way, feel free to kind of stop me if there is a confusion in answer. So now let us try to see some generators generating these pairs. So remember, so the precondition says we want a pair of inputs, a pair of integers such that both of them are greater than or equal to 0. So here's an example of test input generators. So most of these property-based testing frameworks will have these built-in generators. So NatGen, for example, is a built-in generator. And what these generators guarantee is that it will generate all possible natural, for example, NatGen will generate all possible natural numbers uniformly at random. Okay, so the guarantee or a kind of assumption you are making about these built-in generators that these are generating all possible natural numbers uniformly at random. So what this generator is doing is it's making two different calls to this NatGen. So NatGen will generate every possible natural number with uniform kind of probability. And then you are making a pair of these things. So this is one possibility of a generator. And as you can see, this is aligned with the precondition, okay? Because we want two different, a pair of integers which are greater than or equal to 0. There's another possibility of a generator. For example, you can say that I generate one natural number and take a pair of this. This is also note satisfies the precondition. Okay, this is also always going to produce this pair of integers where both of them are greater than or equal to 0. However, if you note that if you try to do property-based testing with the first generator, it's very easy to kind of pass the inputs generated by this and actually hit the bug, as shown here by this kind of reduction. If you actually run this generator, very soon you will actually find this division by 0 exception. On the other hand, if you use the second generator, no matter, regardless how many times you run this generator, you are sure not to hit the bug. And one of the reasons, this phenomenon that this particular generator is not going to produce certain kind of values, is basically could be captured by this fact that if you look at the second generator, it produces pairs of values, but it can never actually cover a pair like n comma n plus 1, which is basically causing the bug to kind of occur. In fact, this generator is too kind of incomplete because it covers a very small domain where every pair is always n comma n. It cannot generate any other pair. So one of the important things about generators is that even if you look at safe input generators, many of them might still lose coverage. And in fact, it shows up in the property-based testing domain. One of the kind of bottleneck in the PBT domain is that as your preconditions, remember this pair of integers greater than or equal to 0, as these preconditions become richer and richer, writing complete or coverage generators or generators which have good coverage becomes harder and harder. And in fact, that is basically one of the motivations why we are interested in this coverage question about test input generators. So with that understanding, I have introduced two important things. So on one side, I'm saying that both these generators, if you look Gen 1 and Gen 2, they are safe. That is, they are always producing these values which do satisfy the precondition, but they do not cover the space which will hit the bug. One of them will not cover the space which will cause the bug to occur. So this I want to kind of highlight one important kind of property which we are interested in. So the second property of the second generator, that it cannot cover this space, is basically a property which we call as the coverage verification question. That is whether a given generator produces values covering a space of values. The other property that it always produces safe values inside a domain is called as a safety thing. So let us try to understand this distinction between safety versus coverage verification. Okay, so safety verification is the most standard notion of verification, which most of us in this group are aware of. So assuming that we have this specification phi, for example, in our case, this is a specification says that these are pair of integers, pair of natural numbers, basically. And on the right hand side is the generator 2. So now the safety verification question will ask this question, that the test inputs which are generated by Gen 2 may only be in phi. That is, every value generated by Gen 2 will always satisfy phi. And if you want to look at more diagrammatically, so the semantics of generated test input or the Gen 2 will be, if these are given by this gray area, so the safety specification is somewhat basically over approximating the behavior of the generator or the test generator. So this is also basically, we understand that this is called phi is interpreted as an over approximation of the behavior of the program. So now let's try to understand the coverage verification question in the same way. So the coverage verification question asks the following thing, that if phi is again the specification of the coverage property, then coverage verification asks that test inputs must cover the space of phi. And diagrammatically, this will look something like that the coverage specification carves out a space of values, the programs you are expected to produce. And generated test inputs, that the generator must produce every possible value covered by this space. Okay. So other way of saying this thing is that the specification, when you are looking into the coverage verification question, your coverage specification is an under approximation of the behavior of the test input generators. When you are looking at the in the safety verification side, your specifications are an over approximation of the behaviors of the program. Okay. So if you use that kind of interpretation, then we can see that Gen 2 is indeed safe because every pair of values it produces does satisfy phi. However, Gen 2 is not coverage complete because as we saw, there are the set of integers of these pairs of integers such that both of them are greater than or equal to 0 will also include all those integers like n, n plus 1, n, n plus 2, and so on and so forth. And this particular generator is not going to produce any of those values. Okay. So now that we have understood the property-based testing test input generators, the need for coverage verification in test input generator and what coverage verification is, we are interested in this automated way of verifying or automated way of coverage verification. Okay. So if you look at the safety correctness question or the safety verification question.
So Ashish, Madhukar here, sorry. So in the last slide, on the right, yeah. So this verification question is about finding a point which is in the blue but outside the gray area, right? Is that what you're saying?
So the coverage verification question is that you want to prove that this term or the input generators in our case basically is going to produce every possible value in the blue area.
So this containment basically is what?
This containment.
Okay.
And as compared to the other thing where you are saying that every possible value is basically so one of the things is this is under approximate is that it can produce other values as well. All I want to prove is that this containment holds.
And you're just interested in the binary answer, yes, no? Of course, with the counterexample, or?
Yes, right now we are just interested in the binary answer. More recent effort is towards giving more probabilistic or answers towards fairness and other things. But right now, in this talk, we'll just do the binary answer.
Sure. Thanks.
Okay. So now
Ashish, can I ask just one question? I'm Abhishek.
Yes.
So all of this discussion is with respect to the precondition in the property, right? I mean,
Yes. So at least in the property-based testing setting, this becomes interesting for the precondition because from various cases. So for example, if your program is manipulating richer data types, let's say trees and graphs and other things, then your precondition will be properties over those things. Okay? We'll see some examples of that as well. So as it turns out, as your precondition become harder and harder, somewhat more complex, then actually writing these generators which are complete with respect to that precondition is challenging. Okay, so that's the point. And but you're right. So this, at least in this setting of the property-based testing, this relates to precondition.
Okay, thanks. Thank you.
Okay, now from the automated, for the automated verification side of it, so how coverage types relates to, so one of the questions we ask is that if you want to build an automated verification machinery for this coverage verification or coverage correctness question, then what is the closest thing in the or approximate world? So as it turns out, if you look at the safety correctness, refinement types give you one automated machinery or automated tool chain to kind of look to kind of verify whether a term has a kind of safety correctness against a given specification. So if you look in the coverage correctness question, then coverage type basically sits in this context. So what refinement types are for the safety correctness in the automated verification world, coverage types are for the coverage correctness question. So this is, in fact, most of this talk will be kind of giving a comparative analysis between refinement types and the coverage type, because we think like that's an easier way to kind of express some of these ideas or show the intricacies.
So, Ashish, this is Raghavan. I had a
Yes.
question.
Yeah.
So generally, it's not possible to generate all possible inputs. Now, all possible pairs of natural numbers, it's not possible to generate that. It's infinite set. So how does one, I mean, how does it make sense to talk about coverage in that way?
So there are two ways. So many of the times you don't want all possible values, but you want some coverage guarantees in a bounded domain. So for example, you might say that I want to generate all possible binary search trees between where the values are between some given values low and high, or if your domain is countably infinite as well, then even then for recursive functions, you can actually prove that this function is going to produce all possible values, again, with a given bound. So it is always, so most of the question, you're right. So I cannot in general talk about that this function is going to produce all possible values in an infinite domain. But many times you are interested in these properties of bounded domains. Yeah. Does it make sense?
So that's interesting, but the bounded domain is different from the countably infinite set. So which of those two are you going for between those two?
So most of the properties, so our language does have recursion, but it is well-formed recursion. So even over there, you are always assuming that there's a fixed depth of your recursive function. So it is, I would say that it is bounded domain is what we are looking at.
Okay.
So because in general, we cannot prove this thing. So definitely we can build a proof using induction argument. But building a type system to kind of prove that argument will be harder. So this particular type system is building a bounded, proving a coverage properties or a bounded domain of values. One way to look at this is that our every figure I'll draw will have this kind of coverage specification capturing a bounded domain of values. Okay, and then I'll be talking about that whether I could cover that. Does it answer the question?
Yes, please. Yeah, go ahead. Thanks.
Okay. So now now that I have set up the context, so we will be kind of now looking into this, talking about some of the features of coverage type vis-a-vis the safety refinement types. And then we will kind of build some of the deeper understanding of how coverage typing differs from, or what are the kind of intricacies in the coverage typing. And then we will talk about some of the implementation and evaluation of this thing. So in order to understand, kind of express some of the more interesting features, let's pick a small language of terms. Okay, so if you look at the paper, there will be more complex language, but for us, let's assume that the terms include these literals. Like for this example, let's only assume that we have literals like integers. There is a non-deterministic choice operation shown as this plus operation, circled plus operation. So a non-deterministic choice operation is an important thing in this domain, because most of these property-based testing frameworks do have these non-deterministic choices. And in fact, most of these questions about coverage becomes interesting only if you have these non-deterministic choices available to you to kind of, it basically makes it more interesting. Beyond that, there are also these standard built-in generators like natgen and intgen. So natgen is basically uniformly at random generating all possible natural numbers, and then intgen is also generating all possible integers. So for this small term language, we can also assume a kind of reduction semantics. So mapping these terms into set of values they will generate. So for example, a literal one will be reduced to a singleton set one. One non-deterministic choice between 1 and 2 will be reduced to a set of 1, 2. natgen basically is represented by a set of all possible natural numbers, and intgen is basically the overall integer domain. Okay, so this is the syntax and semantics, and now let's try to see how do we define concretely define coverage types. Okay, vis-a-vis again using base refinement types. Okay, so traditionally, when you write refinement types, it is mostly written like this. So given that this audience might not be aware of the refinement types in general, so
Ashish, such a simple question maybe. So is that objective is given a type, input generator to check that it does cover the space? Is that the objective? Given the code of the input generator?
Given the code of the input generator.
Yeah, I can't hear Ashish.
Yeah, I think he's disconnected, it seems.
Okay.
Wait for him to come back.
Hello.
Yeah, Ashish, we can hear you. Yeah, we lost your screen and
I think I got disconnected for some reason. I don't know why. So I'll again have to share. Please bear with me. Is it back?
Yeah, we can see
yeah.
it now. You may want to make it full screen, maybe. Presentation mode or whatever. Yeah.
Is this good?
Yeah, I think this is better.
Yeah. Okay. So I think I lost it. So what I was saying is that So to answer Raghuvan's question, I think the goal is that in that direction. But before that, I just want to kind of put what is a coverage type before actually asking this question. How do you actually verify whether a term has that type? And one way to look at this is that if you look at refinement types, and if the audience is new to refinement types, so a typical base, what is called as base refinement type, is represented in this format. And what it has is kind of a tuple or a triplet, and there are certain base types. For example, booleans, integers, lists, or any other base type you can think of from your simply type lambda calculus kind of setting. Along with that, there is a self-reference variable, which is talking about, which references to the term for which this type is going to be assigned to. And along with that, there is these kind of refinements or qualifiers. So for example, in this example of refinement type, mu is equal to 1 or mu is equal to 2 is a qualifier. And if you compare it syntax in terms of syntax, the coverage type looks exactly similar to, and that's by design. It looks exactly similar to refinement types. So in terms of syntax, the difference is that rather than these curly braces, we have these kind of square brackets, and other than that, the way you write coverage type is exactly same as refinement types. So one kind of side effect of this thing is that writing coverage type is not going to be any harder than writing refinement type, say, for example. So, however, now let's try to understand the semantics of coverage types. Okay, so one way to understand the semantics of type systems is that you, given a term, what types it could be assigned to is an important kind of metric, way of understanding the semantics of these types. So here what I'm going to do is, on the top two rows, I'm showing these terms and the values they are reduced to. So basically the values they are reduced to is capturing the exact semantics of these terms, reduction semantics of these terms. And at the bottom, there are set of refinement types and coverage types. And we will try to see for each term what coverage and refinement types could be assigned to that term. So if you look at the literal one, it reduces to a singleton set one. So the first refinement type, which basically precisely captures this behavior, is a valid type for this particular term. Because mu is equal to 1, so because the reduced set 1 is exactly mapping with mu is equal to 1. But as you see, if you look at go towards the right, any weaker type could also be assigned to this thing, this particular term, and which we all understand that in the safety verification question, if a specification could be assigned to a term, then any weaker specification could also be assigned to that term. So the other way of looking at it is that since the value produced by 1 lie within v is equal mu is equal to 1, they also lie within the qualifier, the space of the values carved out by mu is equal to 1 or mu is equal to 2, and so and any other weaker set defined on the right. However, if you look at the coverage type, the only coverage type out of all the coverage types which are given over here, which could be, for this particular term would be the precise coverage type capturing this space of mu is equal to 1. So if you look at the second coverage type thing, where the qualifier is mu is equal to 1 or mu is equal to 2, this particular coverage type could not be assigned to this term because the values reduced to this term is reducing to, that is a singleton 1, does not cover this whole space mu is equal to 1 and mu is equal to, or mu is equal to 2. Similarly, any further weaker kind of specification coverage types with weaker specification could not be assigned to this particular term. So let's try to kind of see if there is a common pattern in this thing. So if you go to the second kind of term in this, it is reduced to these values 1, 2. Now, the precise type capturing this semantics, that is in the refinement world, could be assigned to it. But any weaker type or any type with a weaker specification could also be assigned to this in the refinement type world. However, if you look at the coverage type, the situation is a dual of this situation, where a coverage type with which precisely captures this space 1, 2 could be assigned to it, but we can also assign any other coverage type which has a stronger specification. And the intuition over here is that if this particular term 1 plus 2 covers the space of mu is equal to 1 or mu is equal to 2, that it produces both values 1 and 2, then it is guaranteed to also produce 1. So the coverage notion is that, so one of the important things is that in the safety specification in the refinement type world, if you can assign a type T to a particular term, then you can also assign any type with a weaker specification. In the coverage world, if you can assign a type T to a particular term, then you cannot assign a weaker type with a weaker specification, but you can also assign a type with a stronger specification. And I'm not going to complete this exercise, but in general, what is happening, if you look at the exact semantics, so if I try to formally define what is happening between refinement type and coverage type, so here is what the semantic.
Ashish,
yes,
if I may interrupt, in the previous slide, so I didn't understand what the term does, like the 1 XOR 2 and the NAT gen. What do those terms do?
Okay. So maybe so 1 XOR 2 is basically a non-deterministic choice operator provided by your language between 1 and 2. It's a non-deterministic choice operator. NatGen is a built-in operator which produces all possible natural numbers uniformly at random. So basically what it is saying is that every natural number is guaranteed to be produced by this operator with non-zero probability.
So is the assumption that the term will be invoked repeatedly to generate all the inputs? I mean, each time you invoke the term, it will generate one input. Is that the model? Yeah,
but they have this kind of probabilistic definitions in the sense that once you say NatGen, its semantics is that every possible natural number could be an output of this. So the assumption is that it will be, So one way to look at it is that you iteratively keep on calling them, and then every possible natural number will be generated with some probability.
Okay, fine, thanks. Yeah.
So more formally, this could be said like, if we say in the refinement type world, if we say that an expression E has this particular type, then what it means, or what the interpretation of this is, it could be given by the formula in the bottom, which says that for all values VE of the base type, such that E reduces to this value VE through the reduction semantics of the language, phi must hold on the value produced by it. And this is the standard semantics. And so our exercise on the previous kind of slide could be explained by the interpretation, by a different interpretation for a term type checking against a coverage type given over here. So on the right hand side, if you say that if you can prove, or if you type check that that an expression E has this particular corresponding coverage type, then what it means is that for all values VE, where phi of VE holds, there must be a reduction of the expression or the term E into that value. Does it make sense? So rather than saying that for every value produced by this term, phi of E must hold, you are asking a kind of dual question, that for every value satisfying this phi E, E must reduce to that value. Now here, Raghuvan's question becomes very, very valid, that I'm assuming, so the underlying assumption is that these, somehow I will be able to prove that this holds for all values VE. So it could either hold true because I have an inductive way of arguing about a countable space, or at least in this set of sites is always a bounded set of expressions, values which we are looking at. So I think, just to give me a second, I think I have. Okay, so now let's try to see, with this understanding of the coverage type, an expression having a coverage type, this understanding of what does it mean to have an expression having a coverage type, let's try to understand some of the more intricate features in the coverage type world. So one of the kind of direct consequence of what we saw in the previous two slides is that the subtyping relations in the coverage world is inverted. So typically in the refinement type world, in the top type, that is the type with the top qualifier, that is true qualifier, is basically a super type of all other refinement types. Here, the top type becomes the subtype of all other refinement types. And let's try to understand this thing more. So or the space of integers, intgen is basically a type, is a term which generates all possible integers with non-zero probabilities. So it could be given this type where the qualifier is top. So what it is saying is that intgen produces all possible integer values. Okay. So now if that is the case, then if I look at any subspace of this thing, that is any smaller set of values like all positive integers, then from the earlier semantics, we get this thing that this top type is a subtype of this particular smaller subset of type representing the smaller space of values. And this keep on going to and agreeing to what we were doing earlier, that if I can assign a type, then I can assign a type with any stronger specification to a particular term. So that particular behavior is caused by this inversion of the subtyping relation. And in fact, this could be talked about in terms of this could be talked about in terms of the subtyping relation between contravariant and covariant in case of refinement versus the coverage typing world. So in the refinement type world, the program semantics, that is the reduction semantics and the subtyping relations are covariant, that as you go into weaker and weaker spaces, you go into higher into the subtyping domain. But the situation is reversed in case of coverage types. And the intuition is very simple, because if I can through a term cover a larger space, then I'm also guaranteed to cover any smaller space by the same term. So if I'm producing all values in a bigger space, then I'm also producing any smaller all values in this any subspace or subspace of the values which is in there. Yeah, Abhishek.
Yeah, hi Ashish. I was unable to read this new notation that you introduced here. I mean, when we are going from left to right, we are so this is a subtype relation, or what is this relation?
Oh, yes. So this is a subtyping relation, and I think the previous slide also talked about this. So this particular notation is a subtype relation, and if you are new to this subtype relation, one way to look at it is through the substitution principle. So what it says is that if S is a subtype of T, then any context in which this T could be used, the subtype S could also be could be used.
I see. I see.
So this is
Thank
a
you.
standard substitution principle. You can also think of this as a subsumption rule, which is in this. So basically, what you're saying is that if there is a context in which I can use the supertype element, then I can also use a subtype element in the same context.
Okay. Thank you.
So this is a subtyping relation, and one of the kind of distinctive feature of coverage types is, or basically what is that the subtyping relation is a dual of the subtyping relation in the other refinement type one. So this intuition, I just want to summarize, is that we are always allowed to weaken an over-approximation, that is, grow the set of values an expression may evaluate to, and strengthen an under-approximation, that is, shrink the set of values an expression must evaluate to. Okay, so this is kind of summary of what we have been talking about in the subtyping. Now, another interesting things happens when we are trying to give typing, when we are trying to type functions in this world, okay? And let's try to understand this with an example, what kind of types we can assign to functions. So let's see this example, and here we are having this algebraic data type tree, and along with that, let's assume that we are generating this, we have this generator BSTGen. And what this BSTGen is doing is generating binary search trees whose elements are in the exclusive range between low and high. Okay, so coming back to the original question is that here the generator is tasked with generating these binary search trees, and then you also want to generate these trees where values are in between low and high. Okay, so this is a function. So what kind of type we can assign this function? So one thing we are sure for is that since this is a generator and our goal is to kind of do coverage verification, the return type of the function must give coverage guarantees over given parameters. Okay, so what does it mean? So basically, we must say that whatever is the return type, it should generate binary search trees. It should only generate binary search trees, and it should also produce all possible binary search trees which have values in this range of low and high. Okay, so to do this, we are borrowing some of the ideas from dependent types, which many other refinement types do. So we assume that there are certain method predicates available to you, and this is very common in almost all refinement types. So let's assume we have two method predicates which are checking whether a tree is a binary search tree, and the other thing is other predicate mem is basically given an element and a tree, checking whether the element. What happened? Oh, there is some line on my screen. Oh, okay. It is checking whether whether the element is in member. So now, given these two predicates, I can actually define this specification of the property we want by this predicate phi, which says that given low and high, the output tree is a binary search tree, and the second property is saying that for all integers n, if n is a member in the output tree, then n must be in between low and high. Okay. So now using this, the return type of the function could right away be assigned a coverage return type given by this particular coverage type mu an integer phi v low and high. Okay, so that portion is okay, and this makes sense as well, because whatever is the type I want to give to BSTGen, I want this guarantee that it produces all possible values satisfying this particular specification. Okay, but now the question becomes is what should be the overall type of this function? What should be the how should the shape of this function look like? And for that, we can rely on this important fact that we want this function to be applicable with different arguments. So, and one of the property like you would do in a normal refinement type world is that I should be able to call this function with argument where high is actually low, greater than low, but I shouldn't be allowed to make a call to this function whenever high is less than low, okay? So this additional property I can also assign by saying, okay, let's assume that I can put this additional constraint on the high, the second argument or the second parameter, saying that high is high is greater than low. Together, I can, cutting this short, I can give the following type to the coverage to the function. So BSTGen could be given a type where low is basically unrestricted, and high has this additional constraint that it is always greater than low. And then the return type is what we saw in the previous slide, which was basically saying phi of low, mu, low, high, holds true. So this is the kind of, if we are, the way we defined our base refinement types, this is the most kind of intuitive type we might want to assign to this particular function. Now, there's a problem with this, this particular type, because if you assign this particular type, this is too restrictive to be useful for any function application now. Because look at the term like BSTGen 03, okay? So 0 is a literal, which basically could be given a coverage type given by mu of type integer with mu is equal to 0. Here, the parameter low asks you to give me a term which basically covers the whole of integer space. So 0 is not a subtype of a term 0. The term 0 is not, the type of the term 0 is not a subtype of this particular top type. In fact, by definition, this is a top type, so there is this is the bottom type. So sorry, this is the bottom type, so there is no other term which is a subtype of this term. Okay, so this function is basically useless if I give this particular type. So here again, one of the things is that if we want to precisely assign each of these input parameters coverage types, as you would do in refinement world, the abstraction capabilities of the functions are hindered. Okay, you cannot apply these functions in different contexts. In fact, for each of these applications, I need a precisely a different type, precisely capturing that the input is of that particular type. Does it make sense? Okay, but let's take a step back and think what we want. So given that our goal is coverage verification, what we want is that if the inputs low and high are any number such that high greater than, it has to be high greater than low, given the specification. High greater than low is holds. Then what we want is that this function's body must output all possible values given by the coverage return type value. Okay, and what it translates is that in our setting, the parameter types require some kind of safety correctness. And so what we do in function types, in case of functions, is that the parameters are allowed to have these refinement types, while the body return type of the function is given a coverage type. So in some sense, what it means is that the function type mix both over-approximation and under-approximation, where the parameters are given over-approximate types, because you want that any possible safe value satisfied by that specification is allowed to be passed to the function. But the return type of the function is a coverage type because you want coverage guarantees once this function is applied. And in fact, this is one of the kind of a harder thing to kind of grasp, but function types require you to mix both over-approximation and under-approximation. Now, people who have looked into a lot of this is related to incorrectness logic world. So one of the things, if you have looked into incorrectness logic, this particular mixing of under and over approximate type is not talked in the incorrectness world. One of the reasons is that they are not having these function applications in the original incorrectness logic, but there are further downstream logical works which basically are trying to mix this over and under approximate specifications. So, okay, so we have seen basically base refinement type, function types, and another thing which basically, so what I'm doing is basically I'm going step by step and kind of trying to highlight some of the interesting features of this coverage type checking, okay? And another interesting thing in this setting is this notion of type context, okay? So how we understand...
Ashish, sorry to interrupt, another 10 minutes to wind up.
Okay, I'll try to do that. So another interesting thing is this notion of how we think of type context in the during the type checking world. So let's just try to understand if we are working in the refinement type world. So suppose we want to prove this property that natgen plus 1 is non-negative. Okay, so this could be modeled in the refinement type world by saying that in a context where I assign X having this particular refinement type, can I prove that this refinement type given by refinement qualifier mu is equal to X plus 1 is a subtype of this refinement type capturing natural numbers, okay? Now, if we want to kind of understand this thing, what it means is that every value of X or every assignment of X, this property will hold. So when X is equal to 0, we have 0 plus 1 is actually positive, okay? So when, which is a subtype of mu, of int mu greater than or equal to 0. For each value of X, this holds. So when we have a binding for a variable, so binding for a variable in a safety refinement type worlds in the context basically act like a universal quantifiers, okay? So what this translates to, whenever we say that X has this particular type in a refinement type, for what we say that for all assignment of X, I know that under this context, the thing on the right-hand side holds, okay? The property is a bit different in the, this checking in a context is a bit different in case of coverage world. So let's try to see whether what happens, how the type context behaves when we are trying to see whether natgen plus 1 actually covers 3. So just to start with, this will be modeled by the fact that natgen has this particular type which is given in the context. So X, this has this coverage type in the context. And under this context or binding, we want to prove that, in fact, mu having a type int such that mu is equal to X plus 1 is a subtype of this. Now, we'll see later on that, in fact, this particular subtyping check is correct in this context. But if we actually try to see, just like the previous slide, does it hold for each value X can be assigned to? So for example, when X is equal to 0, 0 plus 1 does not cover, in fact, mu is equal to 3. Same goes for 1 plus 1. And only for X is equal to 2, 2 plus 1 covers mu is equal to 3. So there's a kind of nuance difference here with respect to the type context. So a type binding in the coverage types world is interpreted as an existential quantifier. Okay, so when you say that X has this particular type, what you mean is that exists some assignment of X such that the right-hand side could be proved. Okay, and this basically relates to our earlier interpretation of what does it means for a term to be assigned a type, because what we want to actually prove is that mu is equal to 3 implies under this context that mu is equal to X plus 1. What it means is that, remember, if you actually remember, what we wanted to prove is that for all values of mu such that mu is equal to 3, that is the right-hand side thing which we want to prove, there exists some interpretation of X such that X is greater than 0 and mu is equal to X plus 1. So long story short, the type context behaves very differently in the space of coverage types versus refinement types. In the coverage types, a type context is saying that there exists some interpretation for the X, that is, there is some path in the program where X will have this value. Yeah. Okay. So in the interest of time, I'm not going to talk about function application, but what I would like to talk about is this notion of control flows. Okay, so this typing context being different in the coverage versus refinement types shows up in the control flow cases. So again, when you are doing a safety specification or safety verification, if you have different branches, and let's assume that we want to prove that this particular implementation of BST gen on the left-hand side actually has this type given on the right-hand side. Traditionally, if we are trying to prove something in an overapproximate world, you will assume that every branch should have this type, or basically, or if there is a join of these types such that every branch could be assigned that type. But if you look at this particular, the coverage typing world, each branch, if you look at the coverage of each of these branches, so the first branch basically just covers the leaf element. The second branch, basically, Boolean is a non-deterministic choice. Okay, so this is one way of writing non-deterministic choice between the second branch and the third branch. So the second branch is basically just capturing, again, just producing a single value of leaf type. And most of the values are in fact produced by the third thing. So the coverage type associated, if you want to infer a coverage type for each of these branches, they will not be aligned together. Okay, so there won't be a common join types which will have where each of these branches will have this type. In fact, the control flow is very interesting in this world, because in the refinement type world, you want each branch to have this specification. But in this world, what you want is that something similar to this, that for each branch, if it covers a specification phi1, phi2, and phi3, all you want is that collectively they cover the oral space. And one way of writing this is that phi implies phi1 or phi2 or phi3. So what you want is that if there are n different branches, each of them will cover some space, and collectively they cover the oral space. Okay, that this opens a lot of interesting things, which we because this choice of how you break this your space of terms which you're covering is not predetermined, and in fact you can break it in a lot of interesting possible ways.
Sorry, Ashish, wouldn't you need the opposite implication? That, I mean, so this phi1, phi2, phi3 are the coverage types of the branch, of the three branches?
Yes. So
so then wouldn't you want that to okay, you want
no.
Okay,
so you actually want that because remember you want that the coverage type.
Okay, you have to cover. You want all of these to individually the union to cover phi.
Yeah. So you phi1, phi2, phi3 could cover something bigger as well, but you want at least this thing to happen.
Okay.
So
I think that's fine.
I think this leads to interesting kind of typing semantics, that you can, in fact, type check each of these branches totally independently, and then have this merge function, which basically combines their types. Okay. Again, in the interest of time, I'm not, so I can, in fact, apply this merge function on this example and actually try to prove these are the three kind of specifications for each of these branches. And if you actually apply the merge function, you can actually prove that this function, in fact, has this particular type. Okay. So rather than that, what I would like to talk about is, yes, the algorithm, the type checking algorithm is sound, and the soundness argument is, as we talked about earlier, that for each expression E in an empty environment, if it could be assigned this particular coverage type, then it must be the case that for all values of base type T's, if phi of mu is true, then there exists a reduction of E to mu. That is, there exists some path in my program, because remember, these are non-deterministic programs, such that I can reduce that expression to value V. Okay, so there's a Coq formalizations as well in the paper. And so this is implemented as part of a bidirectional type system, and the type checking is still decidable because we are able to translate these things into these EPR fragment of logic. And I would kind of quickly try to cover the evaluation. So we wanted to type check whether there are interesting properties of test input generators which we can actually verify using these coverage types. So for this, we looked into different property-based testing setups like quick check, and some of the other property-based testing setups as well. Elrond is a random testing setup. And we wrote these hand-written test input generators for many of the problems, these for these kind of quick check for these property-based testing benchmarks. Okay. One of the things is that we wanted to kind of be diverse in the kind of data types we are handling. So we are basically having these PBT setups for lists, trees, queues, streams, heaps, sets, and various different things. And many of these will also by default will require us to have non-trivial properties like membership, non-duplication, sorting, complete tree, red black tree. In fact, if you look at the property-based testing literature, many of these properties, coming up with a complete generator for many of these properties is the community agrees that it is quite hard to kind of write complete generators in these settings. So for example, one of the examples could be that for the size list gen, we want that given a size, we want to produce all list of length less than the size. Okay. So we are diverse in terms of this, and then most of our times are also realistic in the sense that most of the time range between 0.35 seconds to 12.20 seconds to actually verify whether the coverage, whether the test generator has this type. And some of the bigger benchmarks have more branches, and it means more number of tests. So we also have this big case study where we extended it to STLC, and where we basically encode this whole simply type lambda calculus in this.
Ashish, sorry, I missed that in the previous slide. You were able to verify all those programs?
Yes, again for the coverage property of all those programs.
Using your type system.
Yes. And these are big. Some of them are non-trivial programs. For example, red black trees, binary search trees. Most of these generators are non-trivial. They have multiple branches. For example, this binary search tree thing, I suppose, size binary search tree. It has 5 branches, 20 local variables, and so. And it also shows up in our times for verifying. But then we also did this kind of case study where we took this simply type lambda calculus, and we asked and this is available in the quick check setup, which has 13 auxiliary function. And when we ask this non-trivial inductive property, okay, so basically we ask that, can I generate all possible well-typed terms of given context size? Okay, so you assume that you are looking at all possible terms of size up to n, and can I generate all well-typed terms in this calculus? Okay. So I write this generator, and basically I check that this generator actually is able to generate all these terms. And this generator is written by these quick check framework. So this is somewhat much more non-trivial to do. Okay. So the last question we were asking is that, is it even needed? Okay. So if every safe generator, if I just have the safety check and every safe generator is always coverage complete, then we don't need coverage verification. Okay, we just write these generators and check it against the refinement type, and we are done. So in order to kind of make an argument that in fact it is not the case, what we did is we basically so this is just saying, okay, if every generator we generate which is safe is always covered.
Ashish, have you missed your screen? Lost your screen again?
I don't know what is happening, but I'm about to finish this thing. So just give me 1 second. Okay, is it back?
Yeah.
Okay, so to kind of make an argument against this point, what we did is the following. We use the same property-based testing benchmarks. So remember, these benchmarks are all these generators which others have written, and then we have written it in our language. Okay, and we take all these property-based testing benchmarks, and we actually try to use a refinement type-based program synthesizer to synthesize a generator satisfying this specification. Okay, for example, if you are looking at size list gen, so the bottom type is the type of the generator which we will assign in our type. And the top type is basically the refinement type specification, which is exactly the same, just other than this curly braces versus the square brackets. Now, if we use this type and use a refinement type guided synthesizer to generate safe generators, we wanted to ask how many or what fraction of these safe generators are also coverage complete, okay, against the type given underneath. And it is surprising that around 76 to 99% of the generators which are safe, which are generated by these synthesizers, are not coverage complete. Okay, so it is very small fractions of safe generators are actually coverage complete. So this question of actually, do you want to verify coverage completeness of these generators is still interesting. This is beyond whatever the property-based testing community asks. So they are always kind of in the lookout for how to write complete generators. So we do need coverage type checks. Okay? So there are certain future works which we have been building on this. So one extension which we have is by adding.
Sorry, Ashish, in that previous list, you were not able to find proofs using your technique.
No. We were able to prove that it is not complete. So
so how do you do that?
So this asymptotic query is again basically just like you will pass it as a negation of this asymptotic query and try to find a satisfying assignment to that negation. So it will say that, okay, this particular query, there's a satisfying assignment to the negation of this query. So it is, you translate it into these formulas and then you basically.
Okay, so that is not, okay. Okay, fine. Okay.
So yeah, so at that front, whenever our type checker, so when our type checker says that it is coverage complete, what it is doing is it's trying to look at that formula, the verification condition you generate, it negates it, and if it couldn't find a satisfying assignment to that, then it says that, okay, it is coverage complete, okay? Otherwise, if it can find a satisfying assignment to the negation, it gives you a counterexample showing, okay, you cannot, this formula is, and what that formula is, remember that formula is that reduction for all values in this space, there is a reduction, and reduction is well defined in our language. Okay. So there is an extension of this which basically can handle states and other effects. So this allows us to kind of look at stateful and other effectful operations. There is also one possible future extension, which is where remember our coverage type is a binary thing. Okay, I think Madhukar asked this question. It either says that a coverage generator is coverage complete or not, but there is no question of no argument in the probabilistic setting or in terms of fairness. If it covers this space, what is the kind of fairness for a particular set of values it has? There's also, there are some works, not from our group, but there are some works which basically explore this logical foundation of under and over approximate thing, which comes up early on. I think our work was one of the initial works where we had to kind of struggle with how do we combine over and under approximate types in the function application. Unfortunately, we didn't get into it. It's much more nuanced. But read the paper. There's another extension which is basically where we were able to show that you can use this coverage typing plus refinement type guided synthesis to actually synthesize this coverage complete synthesizer. You don't need to verify them post facto, but you can correct by construction, or say you can say complete by construction property-based testers could be generated. So I think this is the setup in which coverage type works. So in the safety world, there's Hoare logic, and corresponding in the type system world, we have these refinement types, which basically uses the underlying logical framework of Hoare logic or other program logics to kind of verify correctness. In this world, we see that this coverage types is a kind of, and we have argued ample number of times now that it relates equivalently to incorrectness logic, or what is also equivalently called as reverse Hoare logic. And so this is the kind of summary of the overall thing. We talked about coverage verification, coverage types, and then we talked about some of the evaluation of this thing. To read the paper, there are some of the things which I couldn't cover is functional application, and some of the things which I have to rush, particularly the type context information. Thank you.
Thanks, Ashish. Are there any questions?
Yeah, Abhishek, you have a question?
Yeah, just go ahead and ask.
Yeah, so Ashish, just one question. I mean, you said when you generated, automatically synthesize this generator from the specification and then tested using, try to verify it using your type checking algorithm, you found that percentage, right? But I mean, where there's some studies on, let's say, a generator written by hands also, I mean, did you also consider in your evaluation, let's say, because most of the time when people write, let's say, generator, they might be a little careful.
I think our main evaluation was towards that direction. Okay, so in fact, we found that many of the generators, so this question whether a generator written by hand is complete or not is not very interesting, because you cannot do it at scale. But many of the times we found that the generators which people have written, we had to kind of add various branches into the generators, non-deterministic choice branches, to make them complete. So in fact, this is a well understood thing in the community, because more recent works has been towards either generating more complete, there's a notion of more in that sense, more coverage complete generators. But there's definitely we found evidence after evidence that the generators people write are many a times incomplete. So, and this also shows up that if you look at the complete, and our synthesis works, the follow-up work talks about this. Many times the generator you will write will be safe, but there will be subtle kind of errors in the program which make them incomplete. Okay, and it's very common to make those errors. That's what the point is.
Okay. Yeah. Thanks.
Yes, please.
Hi, my name is Vadim. What happens if we want to cover not an individual elements, but equivalence classes or some sets, representative of sets? What might change in this theory? For example, in concurrency, we have not an individual elements to cover, but equivalence classes usually.
Yes. So I think one thing which will change is that so underlying this typing semantics is this interpretation of each of these types, so we have to formally define this notion. I think this could be extended in this particular setting. The notion of coverage will have to be defined, is given in terms of what is an interpretation of a type. Okay? Right now, our interpretation of a type is set of these values. We have to map this thing onto this set of equivalent classes in some sense.
Set of sets, something like that.
Yes, set of sets kind of thing. And then basically I think the subtyping relation even now is based on subset relation. So that has to be extended also when you have this set of sets kind of thing. So I think so, but the major changes will come so if you look at the paper, there is this interpretation or denotation of each of these types, which right now maps everything into this set of values, and that has to go into set of sets kind of thing, as you say, or some notion of equivalence classes. But you're saying that is there a domain you have in mind where this could be useful?
Yeah, this is a concurrency domain when you have to cover not an individual elements, but you cover some equivalence classes.
So basically, if you're looking at it as a kind of model checking machinery or many of these things, so many of times you want some kind of coverage guarantees or an equivalence classes. Okay.
You want coverage guarantees. Usually, it's not possible to cover all equivalence classes, but you select some notion and you want to cover some of them, and you want to guarantee that you actually cover some of them.
Yes. I think yeah. So from the top of my head, I think that's the direction which makes sense. Similar questions come in the context when we are using these types to program synthesis, because there we are searching for a kind of representative of a given coverage type. Okay, so I have a coverage type and I want to get one element which could have this coverage type and which I can use in this context. And I think there is some notion of equivalence classes in terms of subtyping relation, not in the exact sense which you are saying. We have to build in that paper. This is an UPSLA 25 paper which is a follow-up work on this. But yeah, that would be an interesting direction. Yeah. Okay. Thanks for the question.
Thank you.
So Ashish, I had one question about the generators. So the generators are they generating things in a random way, or some like one after the other, or what do the programs look like, the generator programs?
So the programs will look a lot like, I think I have one slide. Just give me a second. So a generator even here, so this is an example of a generator, okay? So it will look somewhat like this. So there will be some default generators like boolgen, int, range. So each of these property-based testing frameworks give you these default generators, which internally they are doing something what Raghavan has been suggested, that they basically randomly generating these values out of this domain, and they are not biased in some sense. So you have these random number generators and other things. And the generator is a kind of combination of these default generators along with non-deterministic choice or conditionals. That's what happened. So all these generators, to answer your question very precisely, all these generators are built using these default generators, which are provided by the property-based testing framework. And internally, if you look at these default generators, they will be using some kind of random number generators and and then building on those random number generators to generate random lists, random trees, random other things.
So you would have to argue coverage for those generators, the base generators also.
You assume that those are, so we start, so one way to think of this is that in our type checking framework, we assume that in fact intgen has this coverage type where it generates all possible integers with non-zero probability. Okay, so we assume those things. So we don't kind of prove that the actual implementation of those generators indeed generate this thing. Where it becomes interesting is that one thing which we have missed in this work is that many of these generator libraries also allow you an operator called as frequency, which allows you to bias your generator space. Okay, so you can give some frequency distribution of, let's say you are trying to generate binary search trees, and these are parameters low and high, whether you want to guide it or bias it towards generating more balanced trees or unbalanced trees, those kind of things. So we don't have support for that, but for underlying default generators, we assume that they are complete in some sense.
Okay, and there's no way to really prove those.
I think in order to prove those things, remember internally they will be using some random generator, some random number generator. And in order to prove those property, you need some kind of probabilistic semantics. Okay, so that's what the thing is, that if you want to prove their property, you need more probabilistic semantics for these things. Right now, we have very kind of non-probabilistic, like non-deterministic, but standard semantics.
Okay, so are there any more questions? So
I'm sorry, I don't know why it disconnected two times, but yeah.
Okay, no, that's not an issue. Yeah. Anyway, thanks Ashish for a great talk, and yeah, very nice, very interesting work.
Yeah, happy to talk about
having
it.
You again on VSS for the synthesis part of the work.
Sure. Thanks for giving this opportunity, and thanks for attending. I think it's late. Okay.
Thanks, Ashish. Yeah. Thanks everyone for joining.